We saw when we did an example for the repeated real root case for second-order homogeneous constant coefficient linear differential equations that we had to use reduction of order. And when we did do reduction of order, right, there was a lot of algebra involved, as usual with reduction of order, but the result was actually pretty simple. The multiplier function u was actually just x. It would be nice if there were some straightforward formula for u when you do this reduction of order in this particular case. So let's go ahead and work out what that formula should be. So we're interested in the repeated root case. So our characteristic equation would have to look like this: m minus your single repeated root, which I'm calling m sub 1, squared equals 0, which means your characteristic equation, if you multiply this out, you get m squared minus 2 times m sub 1 times m plus m1 squared equals 0. And then we could translate that into a differential equation that would have this as a characteristic equation. So to go from a differential equation to a characteristic equation, you turn derivatives into m's, basically. So to go the other way, you just turn m's into derivatives. So m squared becomes second derivative, m becomes the first derivative of y, and the constant term, m sub 1 squared, just becomes the term with y with no derivatives. Okay, so because of how we created this differential equation, we know ahead of time that m sub 1 is a root of the characteristic equation, and so one solution to this differential equation is y sub 1 equals e to the m sub 1 times x. And we're looking for a second linearly independent solution so that we can have a fundamental set. And we know how to do this. We're just going to do reduction of order. So y sub 2 is u times y sub 1. So that's u times e to the m1x. And then we have to turn the crank on the reduction of order machine. So y sub 2 prime is going to be u prime plus, u prime e to the m1x plus u times e to the m1x times m1. Let me squeeze that in here. Okay, let's factor out that e to the m1x. So u prime plus m1u times e to the m1x. Okay, and the second derivative is going to be, so now we can just do the product rule on this guy. We get u double prime plus m1u prime. Remember, m1 is a constant, times e to the m1x plus, so first part with no derivatives, so u prime plus m1u times the second part, e to the m1x, with the derivative, so the chain rule spits out another factor of m sub 1. So m1 e to the m1x. And let's combine all of the terms according to the order of the derivative on u. Everything has an e to the m1x. So for second derivatives of u, we have just this one here, u double prime. For first derivatives of u, we have two of them, here and here. Don't forget to distribute that m sub 1. So we have, from the second one, we have, so we have m sub 1 plus another m sub 1. So m sub 1 plus m sub 1 all times u prime. So we'll be able to combine those. And then for zeroth derivatives of u, there's just this one over here. So plus m sub 1 squared times u. Okay, and then combining those middle terms, we get u double prime plus 2m1 u prime plus m1 squared u all times e to the m1x. Okay, now we can plug everything into the original differential equation. Remember, the original differential equation was y double prime minus 2m1y plus, y prime, plus m1 squared times y equals 0. So now we can plug in y2. So y double y2 double prime, that's u double prime plus 2m1 u prime plus m1 squared u, all times e to the m1x minus 2m1 times y2 prime up here. So u prime plus m1u times e to the m1x plus m1 squared times y2, which is way up here, u times e to the m1x equals 0. Okay, now remember we're doing reduction of order, so we need to gather up our terms according to the derivative of u. So there's one u double prime term, and that's right here. I guess first, everything has a factor of e to the x. So divide everything by e to the m1x. Right, these are all gone. So now let's gather up our factors according to the derivative of u. So u double prime. Now for our u prime terms, there's one here and one here. Don't forget to distribute this coefficient. So we're gathering up our u prime terms. So let's factor out the u prime. We have 2 times m sub 1 minus, looks like 2 times m sub 1. So those cancel, actually. That's nice. Plus, now let's gather up our u terms. There's one here, one here, and one here. So we get m1 squared u. We're writing down our u terms, so let's factor out that u. So there's an m1 squared, and then minus 2m1 times m1, so minus 2m1 squared plus m1 squared. And this all equal to 0. So this stuff in parentheses, because we must have done our reduction of order correctly, because all of this stuff adds up to 0, as it should. And so we get u double prime equals 0 again. And since u double prime is 0, that means u prime is a constant, call it c. U itself, integrating one more time, is c times x plus some other constant, call it d. And we can choose whatever coefficients we want to come up with a nice example of such a function u. So we can choose d equals 0, c equals 1, and we get u equals x. So just like in the particular example of the repeated root case, in this general example of the repeated root case, our first solution in the fundamental set came from the characteristic equation, and it was e to the m1x. And the second solution we got from reduction of order, just by guessing u times y1. But it turns out that the multiplier function u is always just x. So it's x e to the m1x. So in the future, if we ever run into this situation, a homogeneous constant coefficient linear second order differential equation, and it's the repeated root case, we know immediately what this multiplier function coming from reduction of order is. It's always just x. Nothing else ever happens in this particular case. So this big calculation that we did to find that u is equal to x, we never need to do that again. From now on, if we ever see the situation, once we know the first solution is e to the m1x, we immediately know the second solution in our fundamental set is x times e to the m1x. Again, I won't check that these are linearly independent. You should do so just by calculating the Wronskian of these two, but you'll find that the Wronskian is always non-zero, and so these two are always a fundamental set of solutions. So the general solution to this kind of second order differential equation is c1 e to the m1x plus c2 times y2, which is x e to the m1x.